Imagine a hair salon with C-service chairs and a total of K spots, including waiting seats. When all K spots are occupied, a new customer turns away at the door and is counted as blocked. Our task is to calculate how often this happens. We represent the system with a Markov chain. Each state K is the number of customers in the system right now, from 0 up to K. Arrivals occur with intensity lambda in every state where there is space left. Note that lambda is constant. Poisson arrivals do not care how full the system is. Departures are different. The intensity scales with the number of busy servers, that is min parentic K, Kc times mu. But notice how the backward arrows grow, mu, 2 mu, and then level off at 2 mu, because we only have C equals 2 servers that can work in parallel. But let us compute concretely. With lambda equal to 3 and mu equal to 1, the forward arrows are all 3, and the backward arrows are 1, 2, and 2. The balance equations say that the flow in between two neighboring states must equal the flow out at equilibrium. We get three relations that express each p in terms of p0. Because all probabilities must sum to 1, we solve for p0 as 4 divided by 61. And here's the gem. Because lambda is the same in all states, the blocking probability is simply pk, the probability of finding the system full. That is the Pasta principle in its simplest form. Many think the departure intensity is always C times mu. That is wrong. Idle servers produce no departures, but the correct curve grows linearly until all C servers are busy, and then levels off. This is the whole difference from MMC with infinite capacity. The structure is always the same. Draw the chain, use the balance equations, normalize, read off the blocking probability. And the most beautiful insight, unlike unlimited queues, we never need the condition ρ less than 1. The finite capacity K makes the system inherently stable. The price we pay is the blocked customers,